Thank you, Mr. Chairman. Good morning, everybody. My name is Guido Zucca. I'm from the chemistry department of the Test Flight Center of the Italian Air Force. And the main duty of my department is failure analysis on military aircraft, not only military and not only aircraft often. And today I want to show you our last investigation about a failure on a cargo ailerons actuator, a failure that involved a military cargo aircraft. First of all, the target of failure analysis is, and also of this investigation, is understand in deep the failure root causes in order to avoid other occurrences, in order to avoid accidents. And in this case, we start with a brief introduction, and then we move to the typical steps of a typical failure analysis, of our protocol of typical failure analysis. And let me introduce you to the framework of the failure. The subject was a cargo military aircraft, and the conditions of flight were ordinary conditions, so yeah, sunny day with no weather involvement and no particular maneuver. So it was a cargo airplane, so it's quite difficult. And the failure involved both hydraulic systems. Many aircraft have, the majority of the aircraft have two hydraulic systems or more for safety reason. And in this case, both hydraulic systems failed. So the involvement was that aircraft have a reduced controllability. Fortunately, due to the skill of the crew, we have an happy ending because they were able to land, refilling the two reservoirs with some spare oil that they have on board, fortunately. And this is the oil plant, and what's happened. We have a rupture on the red line, but the real piece was the actuator, and the dual booster actuator is the main part of the aircraft because it's the mechanism that was responsible of the aileron deflection, so the controllability of the aircraft. And what happened was a rupture on one end of this actuator that involved the two chamfers that are surrounded with the red line, and the two chamfer of the two hydraulic plants. So it was a critical failure because a failure in this position involved the two hydraulic plants and causes the failure of the two hydraulic plants. How is made this dual booster actuator? It is made by two main parts: the piston rod that was located inside the external case, and was closed at the ends with two copper, with two bronze cap, and locked by two screwed retainers. And the actuator is linked to the aircraft by a trunnion. It's a pivoting point and is the only link with the aircraft. The rupture happened on the end of one end of the actuator case, and the end that is closed with the cap, and we find the cap entangled inside, and some force was need to remove the cap without damage the rupture surface, obviously. And was a strange rupture because in this area no controls are provided for the constructor, so it was a quite critical rupture because here that doesn't expect a rupture. Starting with the failure analysis, the first step is a visual and optical optical observation, and we find a rupture surface divided more or less in two halves. The first one, the zone A, the red one, and the zone B, the blue one. The zone A is characterized by a rough and dull surface, 45 degree orientated, and it's compatible with an overload separation. But the zone B, the blue one, showed the typical scene of fatigue. of a multiple initiation site fatigue, the racket marks underlined by the black arrows. And we continue with some observation to confirm about what we see with optical one. So we can assume that the zone A was characterized by an overload separation. We can see the dimples and the microvoid typical of overload separation. And the zone B is clearly fatigue. It's clearly fatigue that that grow from the external edge to the internal one. Also with the electronic microscopy, we were able to measure the striation spacing between one striation and another in order to understand more or less the type of load that generates fatigue. So we find a striation spacing of 60 nanometers, so we assume that is a quite high cycle fatigue. Next up, of analysis, because we know that there is fatigue, we must understand why fatigue propagates, why fatigue generates. And the next step of analysis is the metrologic measurement. And in the metrological measurement, in order to compare it with the design requirements. And during metrological measurement, we find that there is something that doesn't work probably because we find the drawing requirements require a gap between the cap and the actuator case that is between 25 and 100 microns. We find in effect an interference between the two pieces of 25 microns. Is the worst case because the cap had a big eccentricity, so in some combination it fits, but it's quite difficult. And then we proceed with the characterization of the material in order to verify the compliance with drawing requirements. And we perform a chemical analysis with XRF to recognize the alloy, and with the ADS to verify the homogeneity of the alloy. Then a microstructural analysis where we doesn't found nothing of strange, and some hardness test in order to confirm the heat treatment required from design requirements and the mechanical treatment. And the material properties are in compliance with the drawing requirements. So probably the only strange thing is the dimensional non-conformances. Are the dimensional non-conformances that we found with metrological measurement. And we try to simulate the effect of these metrological non-conformances with a finite element analysis. The hypotheses of the finite element analysis are we simulate a perfect fit between between the cap and the actuator case. It's a conservative hypothesis because we find a little interference, and we focus our attention on the materials characteristic because are two very different material and the thermal point of view. So copper alloy for the cap and aluminum alloy for the case, and we apply just thermal load. This is an hard hypothesis, but was justified because only thermal loads have an effect on the dimensional non-conformances. Probably the pressure and inertial load are not an effect on dimensional non-conformance. Why thermal load? Because the oil in pressure works at temperature of between 60 and 90 degrees, Celsius degrees, and the actuator is located inside the cabin of the aircraft, so work about at 20 degrees. So we have a between 40 and 70 degrees of delta T. And the finite element analysis show an abnormal stress, an increasing of stress, abnormal, completely abnormal, located in the area of fatigue initiation. And this is for 40 degrees, so the worst case, probably if we increase temperatures would be better, and we worst under a stress point of view. And after that, we perform a parametrical simulation, increasing the gap between the cap and the actuator case in order to reach the normal stress condition, so sigma 0. And we find that for 50 microns we have the perfect condition, so this is coherent with the drawing requirements. To conclude, the factor surface show a multiple initiation side fatigue that start from the external to the internal edge of the actuator case. And the striation spacing suggests us an high cycle fatigue, and no unusual features were found under the material composition and the material property point of view, but we found metrological interference between the cap and the actuator case. And finite element analysis showed that less than 50 microns would induce an abnormal stress between the two parts. So we end with the cause of the failure. The dual booster actuator failed because of an high cycle multiple initiation side fatigue mechanism that was due to a dimensional non-conformances. And we issue some recommendation to the constructor in order to improve metrological and dimensional controls. This is our chief of staff that reward the commander of the aircraft for the incredible landing he performed. Thanks for your attention.